Alright, today we're talking about 11-7, the areas and volumes of similar solids. Now for two solids to be similar, that means they have the same shape, so like a cone and a cone, a rectangular prism and a rectangular prism, and their corresponding dimensions are proportional. So we have an example over here to your right, over here, and we're going to look at corresponding sides, and it's not necessarily always how it looks. You're going to look at the longest side of those three, or the longest dimension, which is 3 meters, and compare it to the longest dimension of the other one. So we end up with 3 meters compared to 1.5 meters, which gives us, or simplifies to, it's 2 to 1, basically, right? And you can compare all of the other ones. So the medium length side, we can say is 2 meters and 1 meter, which also simplifies to 2 to 1. And then the shortest side, 1.5 meters and 0.75 meters, also simplifies to 2 to 1. Well, that ratio there, that 2 to 1 is, this should remind you of similar polygons and similar triangles. That 2 to 1 is called the similarity ratio. So the ratio of the corresponding dimensions. So I can ask you whether these pictures represent or show similar solids. The first one, we have a diameter of 16 compared to the diameter here of 12. So I'm going to put 16 over 12, and that simplifies to 4/3. So we're going to check to see if the other side lengths, that's 10 over 6, that's the height of this prism, right? Those are corresponding sides. Is that the same thing as 4 over 3? Well, 10 over 6 simplifies to 5 over 3. Therefore, those are not equal, which means they are not similar. And you can look down here as well. We have two rectangular prisms. Now they're facing in different directions though, so let me just create some space here. They're facing in different directions, so again, you can either redraw it where they then look they're lying on the same side, or again, we're comparing the longest lengths, which in this case would be 12 yards and 6 yards, which simplifies to 2 to 1, and then the shorter one would be 8 yards and 4 yards, which also simplifies to 2 to 1, which means they are similar. Anyway, just a note at the bottom, we have, we're noting that all cubes are similar and all spheres are similar. All cubes are similar because they're, if this is a cube of length, let's say it's 3 by 3 by 3, and this one is 5 by 5 by 5, then the ratio for all corresponding sides would just be 3 to 5, 3 to 5, 3 to 5. So, and that's just using 3 and 5. I could have used x and y. It doesn't matter, it's always going to be x to y. Right? So, and you can do the same thing for spheres. The only thing you really care about for a sphere is you're either comparing the diameter or you're comparing the radius. But again, if the radius, if you have one radius, you have the others. So it's going to have the same ratio throughout. So let's look at something here. We're using the same example. Their similarity ratio, we already said, again, going from this shape to this shape, you have to keep the order the same. The similarity ratio is 2 to 1, right? Now, the area ratio, or the ratio of their surface areas, it should remind you, several lessons ago, when you have similar polygons with a specific similar ratio, like A to B, that was the similarity, then the ratio of the areas was A squared to B squared. Well, the same thing's going to happen here. So we're going to get 2 squared to 1 squared, which should be 4 over 1. Let's see if that actually happens. Well, the surface area for this this front shape here would be the area of the base. So we'll call this red part the base. The area of that base, that's what, 3 by 2, which is 6, and then times the height, so times 1.5, which gives us a surface area of 9. Oh, that's the volume. I'm sorry, guys. That's the volume. I apologize. If that confused you, it should have. If it didn't, I'm concerned. It should have confused you because it's not the surface area. It's the perimeter of the base, not the area of the base. The perimeter of the base times the height. Again, sorry about that, guys. And then plus the two bases, right? So the area of the base is 6, which we said, which means the area of the other base is also 6, right? So we know we're going to have 12 for the two bases. Then the lateral area is just the perimeter, which is 10, right? The perimeter of that base is 10 times the height, 1.5. So that gives you plus 15, which would give you an answer of 17. So the surface area was 17 square meters. This next one, and you can figure this out on your own, but the next one will end up being a fourth of that, which is 4.25. So you can check that on your own, and you should get 4.25, which again simplifies to a ratio of 4 to 1. Now the volume of these, again, you may be able to predict it. If the similarity ratio is a to b and the area ratio is a squared to b squared, you may predict what these next two are going to be. But we'll figure it out and see. If we have the volume of these, again, I can do this now. The volume of this rectangular prism is just 6 times 1.5, or 9, right? It's just 9. And the volume of this smaller one here is the area of the base, which again is 1 times 1.5, right? The area is 1.5 there. That's this top figure here. Times the height, so we have 1.5 times 0.75. So I'm just going to do this on the side here. 1.5 times 0.75. I'm going to write 1.5 as 3 over 2, and 0.75 as 3 over 4, and you end up with 9 over 8, right? So we're comparing, the volume there is 9 over 8. If you did that in decimals, you get 1.125. We're comparing 9 with 9 over 8, which, this is 9 over 1 divided by 9 over 8, so you get 9 over 1 times 8 over 9, which gives you a ratio of, these cancel, 8 to 1. Which, it's not just times 2, you're not just looking at, oh, it's double the area ratio. No, it's, in fact, the cube of this similarity ratio. So this is 2 cubed to, let me write it out here so you can see it. We just, whatever you get for your similarity ratio, cube it, and you'll get 8 to 1. Okay? Let's do a couple examples. So, find the similarity ratio of two similar prisms with volumes of 8 centimeters cubed and 27 centimeters cubed. So, the ratio of their volumes we'll write as 27 over 8, which again is just the volume, the first volume, the r cubed, let's put a cubed, over b cubed, where the similarity ratio r is just a over b. Right? Well, then we just take the cubed root of each of these. Cubed root, cubed root, cubed root. And the cubed root of 27 is 3, because 3 times 3 times 3. And the cubed root of 8 is 2. So your similarity ratio would just be 3 over 2. Pretty straightforward. The lateral area of two similar cylinders are 100 meters squared and 144 meters squared. Well, this is the surface, their areas, so we can compare 100 over 144, which again, this is just a squared over b squared, because the areas are squared, where again, r equals a over b. So we take the square root of everything, and we get 10 over 12 equals a over b. But if I want to find the area of the the ratio of the volumes here, I then need to cube it. So I'm going to get a cubed over b cubed, which equals 1,000 over, I forgot to do this calculation beforehand, which would have been helpful. 12 times 12 times 12, 1,728. And that would be the ratio. Now, of course, on a test, you'd have to simplify that. So, anyway. I would like you to try this one on your own, and we'll talk about it in class. So, pause it here, or it's going to stop. Again, obviously you heard the bell in the background again. The strategy here, I'll just go over the strategy real quick. Is there a value for x for which the rectangular prisms below are similar? So again, don't just compare the 80 and the 45 because they're on bottom. That's not the ratio you want. You want to compare the longest lengths with the longest length and see what you get, and then go from there. So that's kind of what you're doing. Think about this one for a little bit, and then yeah, you should be good. Any questions you have, I'll answer in class, or you can leave as comments if you're not in my class. Alright? That's it, guys, so see you later. Thank you.